Today I'll be deriving Kepler's first law the way Newton did it, so without further ado, let's start off with what I proved in one of my previous videos, that the acceleration towards the center equals d theta over dt squared times r minus, that's a squared, gm r squared. Alright, and I proved this in my video on Kepler's second law, where d theta dt times r squared equals r naught v naught equals twice the acceleration over time. Alright, now let's also let's suppose something else. Let's say this r right here equals 1 over z. This is what Newton assumed, and you'll see why later. Let's take a derivative of this with respect to time. So dr dt equals negative 1 z squared times dz dt. Alright. Now we can do something. Let me think. Alright, this just becomes negative r squared dz dt, because 1 over z is r, and 1 over z squared is r squared. Alright, and we know what r squared equals. R squared equals r naught v naught over d theta dt. So we can plug that in here. So if we substitute this r squared into here, we get that dr dt equals r naught v naught with a negative here, d theta dt times dz dt. And now look here, dr dt equals negative r naught v naught. We can flip this around, dt d theta times dz dt, and the dt's cancel out. So we end up with dr dt equals negative r naught v naught dz d theta. Right? And now we can take another derivative with respect to time, and we get this. This is just a constant, so it remains, well, constant. D squared dz d theta squared times dz dt, because times d theta dt, because of chain rule. Alright, now we have two functions of d squared r dt squared, and so let's plug this into here. These are the same, so we get this negative r naught v naught d squared z d theta squared times d theta dt equals d theta dt squared r minus gm over r squared. Alright, now let's convert this d theta over dt into well, from here we get that d theta dt equals r naught v naught over r squared. Let's convert this thing into that. So we get that negative r naught v naught d squared z d theta squared times d theta dt equals r naught squared v naught squared r4 times r minus gm r squared. Alright. Oh, and let's also plug that in here too. So we get that negative r naught v naught times d squared z d theta squared times, well, this squares times 1 over r squared. I move this here. Equals r naught v naught squared over r cubed minus gm r squared. Alright. Now let's divide all sides by this, r naught squared v naught squared, and hence we get negative, and let's convert this into z squared, because if r equal 1 over z, z equal 1 So d squared z d theta squared times z squared equals, oh, whoops, this is a square, and we divided everything, so it should be just z cubed, sorry about that, minus gm z squared over r naught squared v naught squared. And now we can divide everything by z squared. So we get this. Let me see, equals z minus gm r naught squared v naught squared. Whoops, there should be a square. And further, let's rearrange. Let's move this to the right side, or we can just do this. So, and we move this to the left side. So we get this. All right, but now I want you guys to notice something. So we have something, the original function plus its second derivative equals a non-zero constant. So what type of functions can do this? Because let's say z equal, let's say theta cubed. So its second derivative would be 3 or 6 theta. It would be double derivative of 3 theta squared, 6 theta. But however, if we subtract these two functions, we get theta cubed, or if we add them, we get theta cubed plus 6 theta. And this is not a constant. This is not a constant. So what type of function where if you take its double derivative, it cancels out with the original function, leaving a constant behind? Well, to expand on this, there's only one type of function that can do that, and it's namely cos theta. So let's say z equals cos theta plus gm r naught squared v naught squared, and if we take a double derivative, this becomes 0. So dz d theta squared equals, well, negative cos theta, because if we take a single derivative, we get negative sine theta. Derivative of negative sine theta is negative cos theta. So if we add these two together, z plus d squared z d theta squared, we get cos theta minus cos theta is 0 plus gm r naught squared v naught squared. So only a function of cos theta matches what's happening here. Or cos theta can also have a constant in front of it. So let's say there's a constant c. There's a constant c in front of each cos theta. And then we'd get, well, yeah, even if there's a constant c, the second derivative would be negative c cos theta, and they'd also cancel out. So we know that z has to equal, well, it has to equal this constant here, r naught squared, v naught squared, and z just equals this. We know z has to, because due to this relationship, only if z equals cos theta or sine theta, it can equal this relationship. All right? Okay, so now we know z equals this. So that means 1 over r equals gm r naught squared v naught squared plus c cos theta. All right? And that means r equals 1 over c cos theta plus g m r naught squared v naught squared. And this is the form of an ellipse. That's the form of an ellipse. If r equal, in polar coordinates. If r equals this, then in polar coordinates, then this is an ellipse. Thank you. That's Newton's proof. All right.